Yeah, after my clock, it's time now. Good afternoon, ladies and gentlemen. My name is Oliver Pust. I am with Delta Optical Thin Film, and today I will talk to you about linear variable filters for fluorescence diagnostics, hyperspectral imaging, and spectroscopic applications. So what you will see are applications and details about these filters. You're also welcome after the presentation to visit our booth 322 just down this aisle. Before I begin, I'd like to show you what I will mention. Who and where is Delta? Principles how we construct and produce our filters, some advantages of our thin film coatings, and then I will go into medias res and talk about how to use linear variable filters for spectroscopic fluorescence applications, show you some narrow bandpass filters, and also discuss with you what we have as plans for the future. The roots of our company go back to 1941, and the ones who know us are probably more familiar with that logo, the red one. Recently there was a management buyout backed up by some very interesting investor. So the thin film business, the filter business of Delta, is now a company on its own called Delta Optical Thin Film with the new logo. We are headquartered in Denmark, close to the capital of Denmark, Copenhagen, and worldwide we work with distributors. We are nowadays the leading supplier of linear variable filters and otherwise are specialized in custom designed optical thin film filters. A little bit background where we come from. Delta was actually the one who suggested to use interference filters for fluorescence microscopy in the late 60s. At that time to Carl Zeiss and Leica in Germany. And in the 70s we began to produce fluorescence filter sets in large volumes for these OEM customers. And nowadays it's still our biggest business area, but eventually during the next few years it will be overtaken by the linear variable filter business. We very early implemented computer-controlled deposition of thin films to be able to fulfill the ever-increasing demands of our customers. And during that time we also developed our own deposition control software and our own design software. These two software packages are tightly integrated, and that allows us to do some things which can't be done with standard software and standard deposition chambers. So we focus on making high quality filters like you do with ion beam sputtering, but in a larger volume so that we can offer very attractive prices to our OEM customers. Before I show you LVF filters, I can't spare you for seeing some of our high performance fluorescence filter sets. On the left hand plot you see a typical fluorescence filter set in transmission scale. You can see very high transmission level, very steep edges, very low ripple in the pass band. So these are actually measured curves. And on the right hand side you see the blocking curve in logarithmic scale. And you can see that we, without any problem, can achieve OD5 or even OD6 blocking if that is required. And also our dichroics are kind of special in the sense that they have a broad blocking range and support with at least ODT blocking for the emission. All our modern constructions are unglued filters without any color glass. And for our dichroics we can actually apply a stress compensating coating on the backside to keep the thin dichroics flat for good imaging quality. The coating is durable and stable, so it can be tooled after coating to whatever size is required. This slide shows the principal difference between a classical filter and a linear variable filter. On the left hand side you can see how on a glass substrate the dielectric multi-layers are coated, and the aim of course with classical filter is to have the coating thickness as uniform as possible across the whole batch of filters. And if that layer stack then represents a bandpass filter, we get one center wavelength and one bandwidth across the whole filter. What we now do with our LVF is to modify the deposition rate in the coating chamber in such a way that we get a linear gradient across one dimension of the substrate. And with the changing thickness of the interference layers, also the wavelength characteristic changes continuously along the filter. And if that layer stack of many more layers, of course, represents a bandpass filter, we get a tunable bandpass filter where the center wavelength is a continuous function of position along the filter. So these are not 10 discrete bandpass filters. This is actually the measurement of a linear variable continuous filter at 10 positions on the filter. But as you move along, the center wavelength changes continuously. The advantages of our filter constructions, as for our classical filters, is ultra hard coating on fused silica substrates that cause minimal autofluorescence and also give you a high laser damage threshold. So the filters work very well with the supercontinuum light sources that become more and more popular. They use as wavelength selector there. For all the filters, the transmission is mostly higher than 90% or even more. The blocking is to be designed OD3 or better. And if you want higher blocking, you can add a second filter to almost double the blocking, for example, for fluorescence applications. Unlike other vendors on the market, we have a complete family of linear variable filters. So we have different long wave paths, we have different short wave path filters. We also have a dichroic that is optimized for 45-degree angle of incidence, and that allows you to make an epifluorescent setup. And we have different bandpass filters that cover the wavelength range from 320 nanometer up to 1000 nanometer. And besides the hardware products, we also can offer helpful application notes that are based on our simulation software that help you make optimal use of the LVF filters in a given optical setup. On this slide, I give you an overview of what our filters are being used for, and there are different application scenarios. So the first one is that you put a long wave path and a short wave path filter on motorized stages, and in this way you can realize, for example, a wavelength selector for broadband light sources like supercontinuum lasers or xenon flash lamps or other broadband light sources. They are used for blocking the higher orders of grating-based instruments, for example, in fluorescence spectrometers, and for suppression of stray light. And you can also use these filters, and that is being done to develop spectrometers which are purely based on filter technology, which gives you very high sensitivity and very good signal-to-noise ratio. As mentioned, we have the dichroic, and if you include the dichroic into the motorized setup, you can design epifluorescence measurement systems which are purely based on filter technology without any grating. And then you have the situation where you put the filter in a fixed position with respect to your light source and or detector. And in this setup, they are, for example, used as small order sorting filters for the well-known compact spectrometers. And the advantage is, compared to other order sorting filter solutions, that they are not discrete, but that they have a continuous function without any step in between. What you can also do is you take our bandpass filter and combine the bandpass filter directly with a line scan sensor or imaging scan sensor, and that gives you either a compact spectrometer or a hyperspectral imaging detector. Here we take a little bit closer look at one very interesting application example that is made by the company BMG Labtech. You find more details on their website. They have realized a fluorescence microplate reader purely based on filter technology instead of gratings. So what they do is they have a broadband light source, the xenon flash lamp, and in that black box, what they call an LVF monochromator, they have motorized sliders with some apertures, a short wave path and a long wave path tunable filter, and also some discrete filters for the deep UV applications. With the LVF monochromator, they can filter out the exact optimal excitation wavelength for a given fluorophore. That wavelength is reflected by our dichroic down into the microplate well, and the fluorescence emission comes back through the dichroic, is transmitted into a second LVF monochromator that is tuned to the optimal emission spectrum of the fluorophore. And I think by now you might have read what advantages they can achieve compared to conventional microplate readers. On these slides, we take a closer look at the spectral performance of our filters, and here you can see why it is now possible using LVF for serious applications like fluorescence. On the left-hand side, we have the transmission plot, and on the right-hand side, the OD plot. And again, you can see we have very high transmission levels, very low ripple, steep edges, and a broad blocking range. And the blocking, again, is designed to be at least OD3 absolutely closer to OD4 actually. And the blocking comprises the whole tuning range of the filter. Here you see a comparison with older technology that is still on the market, and here you see the obvious reason why previous technology filters cannot be used for fluorescence. It's not so much the ripple and the lower transmission level, but it's the edges which are not steep, but even worse, these leakage effects in the rejection band which render fluorescence measurements impossible with these old technology filters compared to the filters that we produce these days. Here we have the short wave pass filter. It's basically the mirror image of the long wave pass, although there in principle is a little bit higher ripple in the pass band, but again steep edges, high transmission levels and deep blocking. And here the comparison with older technology is even more striking. So you really have to look closely to recognize the short wave pass filter. The transmission drops rapidly away from the edge. It's not steep at all, and then again severe leakage effects in the rejection band. In this animation, I show you how you can combine these two filters to make a fully tunable bandpass filter by moving them with respect to your light source. And in good optical practice, you want to angle them a little bit to avoid interreflections. And in the first sequence, we move the filters synchronously through the beam path, and that changes the center wavelength continuously between 300 and 850 nanometer. And in the second sequence, you can see when we move the filters in opposite directions, we adjust the bandwidth again continuously between as narrow as 10 nanometer and 150 nanometer or more. So with just two optical components, you have any bandpass filter between 300 nanometer and 850 nanometer. And you can also see the top line is 100%, so very high transmission level throughout the complete tuning range. And again, the comparison with older technology. On the left-hand side, you see if you want to make a band of 20 nanometer, your transmission already drops to about 50–60%. And if you make it even more narrow, you get even less transmission because of the very sloppy edges. If you want to have at least 80%, you need to make a 40 nanometer wide band. And as you recall, with our solution, you can make 10 nanometer bands at full maximum transmission, about 90%. Here we have another application in fluorescence spectroscopy that I also mentioned earlier. So it's a typical L-bench setup of a big fluorescence spectrometer that typically uses a double monochromator grating or single monochromator grating. And in this setup, the grating was complemented with a tunable bandpass filter. So the primary wavelength selection is done by the grating, and then the tunable bandpass filter is centered around the emission of the grating. And what that yields, I will show you on the next slide. And the same setup is also done on the emission side. Here the red curve shows the results of Raman measurements of cyclohexane without the filters. That means one monochromator, one grating. You see the signal peaks and you see the noise floor. And if now the noise floor is too high, the signal to noise ratio is not good enough, you can use a double monochromator, which makes your spectrometer very bulky, expensive and very sensitive. And then you get the blue curve, which gives you a nice clean noise floor. But of course your sensitivity, your signal strength has dropped quite a lot because of the second monochromator stage. Now you take one monochromator and add our tunable bandpass filter. That gives you the green curve. And because of the very high transmission level of our filters, you still have the same signal strength as with one monochromator. But because of the high out-of-band blocking of our filters, you get a noise fluor that is on the level with the double monochromator. So that combination gives you the high sensitivity of one monochromator and the signal-to-noise ratio of a double monochromator without being as complicated and expensive as a double monochromator solution. If you're interested in more details, there's a publication on our website for download. Now let's go away from the edge filters to the bandpass filters. That was our first bandpass filter, or is. It's a filter for the visible range from 400 to 700. Broadband blocking exceeding the tuning range of at least OD4, and bandwidth that is slightly higher than 2.something% of the center wavelength. And again, no metal layers, no glue, no color glass, makes also this filter applicable for laser applications. Once more, comparison with older technology. On the left-hand side, you see a so-called induced transmission filter that uses thin metal layers. That on one hand limits your peak transmission, but it also renders the filter impossible for laser applications. It will absorb the laser energy and simply burn. And again, on the right-hand side, our filter, much steeper edges and much higher transmission at any given wavelength than previous technology. Even more important, look at the blocking curve, the OD plot. Old technology, and you can see that the edges are far from steep, the blocking level is inconsistent, and you also have some leakage effects in the blue region. And for comparison, again, our filter with a nice deep blocking level of better than OD4, absolutely. We added a near bandpass filter covering 550 to 1000 nanometer with the same characteristics as our visible bandpass filter. And the most recent addition to our product range is a more narrow filter for the visible range that now has a bandwidth of 1% of the center wavelength, which makes it applicable to even more spectroscopic applications. And here again, the same very good blocking behavior as for our previous version of the bandpass filter. So what can you do with these filters? Of course, you can also use them for spectroscopic applications by moving them through the light path. But another idea is to combine them with imaging sensors or with a line scan sensor. Here the example is a line scan sensor, and here we have different configurations with imaging sensors. And in this case, you have a very compact and robust and light efficient mini spectrometer. And in these configurations, you have a hyperspectral imaging detector that works with the push-boom technique like known instruments, but which is much more compact than if you had a grating or a prism, and also much more light efficient. These statements over here are actually not mine. These are taken from some publications from a group in Munich who have used a linear variable bandpass filter to make a point spectrometer, but also to make line scan spectrometers. And compared to a grating, it has a much higher aperture, so you collect much more light. It has a higher transmission efficiency, which allows you for a shorter measurement time than if you would use a grating. Also, the suppression of stray light is at least one order of magnitude better than with a standard grating. And you have the very high signal-to-noise ratio. So, what plans do we have for the future? Actually, right now we are coating a linear variable bandpass filter that extends the wavelength range into the UV, further into the UV, I have to say, starting at 320 nanometer and going up to 540 nanometer. So now we can cover all the ranges from 320 to 1000 nanometer with these different filters. We also have designs ready for production that extend the wavelength range of our edge filters either to 1000 or to 1100 nanometer. And of course we are aware that there are many applications in the near infrared, a little bit closer to micron. So that is something we are interested in, but I can't promise a concrete roadmap because that requires some heavy modification of coating technology to be able to achieve that longer infrared wavelength. So let me conclude my presentation. We can proudly say that we have lifted the application range and the performance level of linear variable filters to levels that make them applicable to serious applications like fluorescence. The filters are coated on fused silica substrates, monolithic constructions with very low autofluorescence and high laser damage threshold. And all these filters are available as standard components from our web shop. And of course, again, we are mainly involved in customizing filters, so if you have specific needs, we are happy to take a look at that. So thank you very much for your attention. There's still time for questions and more in-depth discussion at our booth, just right down a few meters with the 300 aisle. Thank you very much.